Hello, I'd like to take you on a technical walk around a Robinson R22 helicopter. I'm using the Beta 2 as this is predominantly the one used in the training environment. I must point out that whilst doing your pre-flight inspection, you use either the pilot's operating handbook or a check card. Let's have a look at the front of the helicopter. Firstly, we want to have a look at the conditions of the windscreen,
looking for damage that will affect your forward vision.
Just checking that our turn and slip indicator is still attached. Coming further down the windscreen, again looking for damage that's going to impair your vision during the training sortie. Coming down to the chin area, we're looking for security of the landing lamp. Again, looking for this area for damage. Right the way round to the forward right-hand undercarriage attachment. Right, let's look inside the cockpit. The first thing we need to do is switch the battery on. Checking the warning lights that should be on are on, the gauges are reading correctly. Now it's most important that your carb air temperature gauge is reading the same as your outside air temperature gauge to make sure that when you have carb heat applied during cruise flight that you have enough applied to prevent the engine from icing. To check the landing lamp, we need to turn on the battery master switch, the landing lamp switch on, the clutch switch in the engaged position, and check the reflection on the ground. There are currently 3 engine start inhibitors fitted to the Robinson R22. The first one is the clutch switch. If that is in the engaged position, you will not be able to start the engine. Secondly, if the horn circuit breaker is popped or pulled, you will not be able to start the engine. And thirdly, if the rotor brake is on, there is an amber light to tell you that it's on, you will not be able to start the engine. The other warning lights we need to check are up here. And we can do that from the right-hand side of the aircraft. The test switches for the warning lights in the cockpit are located underneath the cowling, just here. And if we press the main rotor temp switch, you can see the corresponding light coming on in the cockpit. And likewise for the main rotor chip, the tail rotor chip, and the low fuel warning light. You will notice that there was a delay in the low fuel warning light coming on. This is there to prevent the light from flickering when we do have low fuel. Now we need to switch the battery off to conserve the power. Now let's have a look at the seat assembly. The first thing to remember is it's important not to have heavy, sharp objects under the seat. The seat is designed to collapse during a heavy landing, and if you do have hard objects under the seat,
That's going to remove the seat's ability to protect your spine from the impact of a heavy landing.
Now it's important to make sure that any passenger knows how to release the seatbelt. And they must understand that you have to pull the latch through 90 degrees to get the seatbelt released. Now let's carry on with the rest of the external inspection. Starting with the door, we're looking at its general condition, making sure that the upper and lower hinges are split-pinned. This is actually an airworthiness directive, and if not complied with, will invalidate the C of A. Coming off now, we reach the auxiliary fuel tank and the fuel cap. Taking the fuel cap off, we can see this one actually has a chain. Some of them don't have chains. Either is acceptable. However, if you do have a chain, it is imperative that the fuel cap is on and the 2 witness marks are lined up. If you leave one of these chain fuel caps off, then when you're flying, the chances are the fuel cap will depart from the chain and end up in your tail rotor. We will now want to come down to have a look at the fuel sample check. Opening this panel gains us access to the auxiliary fuel tank drain, identified by this yellow pipe. Pushing up on this valve will allow us to take a sample in a suitably clean container from this position here. Having taken and checked the sample from the auxiliary tank, we need to do the same with the main tank. The main tank is situated on the left-hand side of the aircraft. We have a similar fuel cap, and the drain valve is just here. Pushing in on the drain valve will allow us to take a sample, which we need to check, before going down to the gascolator. Pushing up on the yellow tube will allow you to take a sample of fuel. So here we have an example of uncontaminated fuel. What you're looking for contamination are small particles suspended within the fuel. And water. If I add some water to the fuel sample, you can see water being heavier than fuel will be at the bottom of the container. That concludes the sampling checks. Now let's check the contents of the fuel system using this dipstick supplied. Dipping the main tank, we check the contents indicated on this dipstick against the contents indicated within the cockpit. Now let's continue. Okay, let's have a look at the main rotor gearbox area. The main rotor gearbox can be found underneath this cowling here. So if we look inside, we can see the sight glass, we can see the decal telling us what the level should be. Above that, we can see a teletemp, and at the bottom of the gearbox, we can see a chip detector. Now over here, I have a main rotor gearbox just to allow you to see things a little bit easier. Now we can see more easily the sight glass of the main rotor gearbox, and we would see the oil level in there, which we can check against the decal to the right of it. Just above the decal is the teletemp. So if the main rotor gearbox feels a temperature of 104 degrees, then the box here will go black. If you see a black box like that, then you need to talk to an instructor or an engineer to make sure there was an operational reason for the temperature to increase to 104 degrees. If you're satisfied that it was operational reasons, then you should put a black line to the right of the box. If after you've been flying again, the component feels a temperature of 110 degrees centigrade, then this box will go black. And again, you would check with an instructor or an engineer that that was for operational reasons, and if you were happy, you would draw a line, and so on. There are 7 teletemps fitted to the R22 helicopter. We have one under the pilot's seat, one on the main rotor gearbox, as you can see here. We have one on the forward drive shaft, just adjacent to the upper sheave. We have one on the upper sheave bearing. We have 2 on the lower sheave bearing, and 1 on the tail rotor gearbox. Under the gearbox, we have a chip detector. We have 12 volts going to the chip detector via these 2 wires. The centre electrode here is magnetic. The magnet would attract a chip of metal. The metal chip will cause a short circuit, putting the light on in the cockpit. Let's look at how the dual tacho gets its main rotor RPM information. Here we have the input yoke. On the input yoke we have 2 magnets. Attached to the gearbox we have 2 sensors called Hall effect sensors. These will sense the passage of these magnets during rotation. One of the Hall effect senders gives us rotor RPM information in the cockpit. The other one gives us low rotor warning horn and light information. Just here we have the temperature sensor for the main rotor gearbox. Now we have a number of flex plates on the aircraft. This is the forward flex plate attached to the forward input yoke. Now, because the drive system is misaligned when it's disengaged, these flex plates are under stress. The area that we're going to get cracks are along these edges here. So because this flex plate is under stress, you're going to feel the edges of the cracks when you run your finger along there. Before we go back to the aircraft, let's just have a look inside a main rotor gearbox. This removed section here allows us to see the set of spiral bevel gears within the gearbox. Here we have an input assembly comprising of an input shaft, which is splined, a bearing and a set of spiral bevel gears. It's all splash lubricated, there are no oil jets within the gearbox. And back to the aircraft. The main rotor gearbox is air-cooled via the engine cooling system through this hose. Looking around here for oil leaks from the main rotor gearbox. From this fuel line, we're looking for fuel leaks indicated by a blue dye in this area here. Security of wiring looms. We're checking for cracks in the upper frame around weldment areas like this. The tail rotor push-pull tube, we're looking for freedom of movement and security. Going inside, we have the main rotor drive shaft going forward into the main rotor gearbox, and we need to check the rotor brake assembly for correct operation. And coming up here, we have the static source for the instruments. Going back down onto the drive shaft, it runs aft into the upper sheave. There's a teletemp on the drive shaft situated just here. The upper sheave holds the freewheel unit. This runs in red Dextron transmission oil. There is no sight glass, so you can't tell what the level is. It has two seal plates, one forward and one aft of the upper sheave. Should this assembly leak, it's going to centrifuge oil along this cowling. We come on to the drive belts. We need to check for damage of the drive belts. If we push the belts in just here and rotate the upper sheave towards us, looking for nicks, cuts and frayed edges. Then coming aft, we have the upper sheave bearing. This is a ball bearing running in grease. If this bearing gets hot, the grease is going to melt and dribble from the seal just here. As you can see, it has a teletemp. This is a prime example of a teletemp being inaccurate. In other words, we have a block here that's gone black. It's missed a block, and this one is starting to shade. This teletemp would need to be replaced. On the drive shaft just here, we have a witness mark that runs between the drive shaft and the inner race of the bearing. This allows us to see and check that the inner race of this bearing isn't slipping on the drive shaft. The upper sheave bearing is attached to the actuator. We're going to have a look at this off the aircraft. This is the actuator assembly with the actuator just here. It tensions the belts. The lower part of the actuator is attached to the lower sheave bearing and lower sheave. The lower sheave is bolted directly onto the crankshaft. The upper part of the actuator is attached to the upper sheave bearing. The drive is transmitted via the belts to the upper sheave, forward to the main rotor gearbox, aft to the tail rotor gearbox. Okay, let's have a look at how the actuator works. The pilot will operate the clutch switch in the cockpit that will cause the motor to drive the upper sheave away from the lower sheave. The belt tension is controlled by two sets of column springs operating two micro switches here. Should the actuator try and over-tension the belts, this piece of wire will become taut operating the over-travel limit switch. The indication in the cockpit will be that the amber light stays on longer than normal, causing the pilot to make a precautionary landing. Let's have a look at the actuator continuing. Now what we're looking for is the belt tension reaching the point where the column springs will operate the two micro switches. The light will then go out in the cockpit. Let's have a look at the actuator disengaging. The pilot will operate the clutch switch in the cockpit to the disengaged position, putting the light on in the cockpit. That tells him that the electric motor is now driving the upper sheave towards the lower sheave, detensioning the belts. The controlling microswitch is now the down limit microswitch, which is controlled by this plunger. And adjusting that plunger will allow us to change the slack on the belts for starting purposes. When the actuator is fully disengaged, the light will go out in the cockpit. Let me give you a scenario. The pilot operates the clutch switch in the cockpit, tensioning the belts. The only time the pilot knows he's ready to go flying is when the light goes out in the cockpit. What happens if there's a fault with the electric motor? It would blow the circuit breaker, putting the light out in the cockpit. The pilot now could go flying with a partially engaged rotor system. To prevent this happening, we fit an inline fuse. Let's have a look at what the inline fuse will do. I will re-engage the circuit breaker. Now, if the fuse blows, the motor stopped, but you'll notice more importantly the light stays on in the cockpit, preventing the pilot from flying with a partially engaged rotor system. Let's have a look at the intermediate flex plate. This is the intermediate flex plate as fitted to the aircraft just aft of the upper sheave. The flex plate needs to be inspected just as we inspected the forward flex plate. You will note that there is a cut in all these flex plates, and that is there just to show me that this is a training aid only. Coming back to the aircraft, we just now need to secure the panels. We have an engine fitted cantilevered facing aft in this airframe. It is a Lycoming R22 B2C normally aspirated engine, rated at 160 horsepower. However, in this airframe, it is rated at 131 brake horsepower for 5 minutes and 124 brake horsepower max continuous. This is done by controlling the RPM and the manifold pressure limits. Let's have a look at the engine area. Checking security of the exhaust system, the inlet manifolds, the spark plugs, the oil drains from the rockers, the cables running up to the spark plugs, looking generally for excessive oil leaks. We have here the inlet hose to the airbox, checking for damage and security. Next to it we have the inlet to the airbox from the carb air scoop. We get our carb heat from the exhaust system gathered by this shroud here. The corresponding edge, this sharp edge around here, is very close to these oil pipes, so we must make sure there's a gap between the edge and the oil pipe. Inside here we have the cylinder head temperature probe. This is number 4 cylinder and it's the furthest away from the cooling system. These oil pipes run all the way aft up to the oil cooler. We need to check this area for cracks. So here we have the aircraft to engine bonding leads, the crankcase breather with holes here to allow the crankcase to breathe should the breather ice up in here. We have holes drilled in it all the way up, and so we get oil mist from the breather onto this area of the engine. The starter vibrator sends a high-intensity shower of sparks to one spark plug in each cylinder during the starting sequence. Just inside here, fitted to the bulkhead, is the alternator control unit. Now onto the right-hand engine frame, looking for general condition. Round the weldments here, coming onto the undercarriage, looking at the general condition of the undercarriage on this side of the aircraft. Then we're coming aft, onto the engine cooling scroll, looking for general condition again and security. Up onto the tail boom, we come down looking for dents and damage, running your fingers over the rivets That will tell you if a rivet is loose, also looking for the black paste or dust produced by a fretting rivet, an example we'll have a look at now. Here's a good example of a fretting rivet. You can see the black deposit around the rivet head, caused by the rivet head rubbing against the skin. Coming further down the tail boom, we're checking the security of the strobe light. Down to the empennage, checking the vertical and horizontal stabilizer. Check the leading edges for damaged dents, as well as the trailing edge. Then onto the rear flex plate. To inspect this, we need to pull down on the tail boom. If you're on soft ground, we're going to have to previously fit the wheels. Now we look through the inspection hole whilst rotating the tail rotor blades to make sure that we can see each of the 4 attachment bolts, checking for security of the nuts to the bolts. That is indicated by a witness mark running across the nuts. Allowing the tail boom to come up gently, we now want to come round and check the stinger for security and making sure it's about waist height for the average sized person. This is going to give us an indication of a possible heavy landing, and the damage is going to be caused back here by the undercarriage splaying out, creating what we call a smile on the rear cross tube. Back up to the rear of the aircraft, we want to carry on by checking the security of the rear position light. Coming onto the tail rotor gearbox, you check the oil level of the tail rotor gearbox through this sight glass. You'll notice the oil is coloured blue, just as it is in the main rotor gearbox, and also the vent up here. This vent allows for the venting of the gearbox during operation. Come on to the tail rotor bell crank. You want to make sure this is full and free, also operating the pitch change mechanism here and the tail rotor blades. And onto the tail rotor pitch link here, we have 2 types, the single piece or the 2-piece. Here we can see we have the 2-piece. We're going to check each bearing now for play. We're looking for axial and radial play. These bearings should be free without looseness. So here is actual play, and we're allowed 20 thousandths of an inch in that direction. And in radial, we're allowed 10 thousandths of an inch. So each control end should have a special washer. This will prevent the bearing, should it fail, coming off the control, in this case the tail rotor pitch arm. Each bolt should have a nut and a pal nut and a witness mark showing its integrity. Coming down onto the tail rotor blades now, we want to have a look for possible damage of the blade. Looking along the leading edge of the blade for nicks and dents, as the skins as well. Coming up now to the delta hinge assembly, what we want to do is operate the delta hinge assembly here, making sure that this bolt head here doesn't rotate during the operation. The limit there is 5 thousandths of an inch, which means if you can see it, it's already exceeded that limit. Again, we're looking at general security of the nuts and assemblies up here. Coming round to this side of the gearbox, we have the output seal just here, and any leaks will be evident by oil dribbling down here. The input seal is a little bit more difficult to see because that's hidden by this casting. However, if we operate this bell crank, we'll be able to see oil dribbling onto this push-pull tube.
Here we have the tail rotor gearbox chip detector. Remember, that works in the same way as the main rotor gearbox chip detector, attracting metal particles to it, causing the light to come on in the cockpit.
Now let's have a look at this side of the tail boom, looking for dents and damage, as we did on the other side, loose rivets, right the way down to the juncture of the upper frame. Looking at the weldments on this side of the frame, just as we did on the other side for cracks. We have the lateral centering tie rod just here. We have this side of the cooling scroll, looking for security and damage, then into the cooling fan. The important thing is to make sure that this roll pin here, which has the locking wire going through it, is in line with these witness marks on the base plate. We also want to check security of these nuts. If they're loose, you'll get the red rust dust produced just underneath them. And also we're looking for cracks emanating from these weldments here. Now coming to the left-hand side of the engine, we need to go into here to look at the lower sheave bearing and the teletemp and any extruded grease from the bearing. The alternator, it's belt driven and there's a spare belt tied up on top of the crankcase for use in emergency. The alternator is air cooled. Fitted to the underside of the engine is the carburettor, into which is fitted the carb air temperature probe, giving us the indication in the cockpit. Now looking at this side of the engine, we want to have a look at oil leaks, security of the exhaust system, the inlet manifold, the drain pipe from the rocker cover here, the ignition harness, inlet manifold pressure takeoff. We have a drain here for the engine oil sump. We have a battery box holding a 12-volt battery, a negative lead, a positive lead. We have the battery relay just here. We can jump start this aircraft, putting the negative onto this lead here and the positive underneath this orange boot. Now you should never go flying with a totally flat battery, because if you should do so and have an alternator failure, the alternator will not have sufficiently charged the battery to allow the electrical indications within the cockpit to continue. This, of course, means that you will lose all your warning systems and all gauges. Let's go into here. We have two transducers. They give us engine oil pressure indication and low oil pressure warning.
It also gives us oil pressure to operate the Hobbs meter.
Up here we have the cabin heater motor. You'll notice on the side of the airframe we have two decals. The top one gives us the amount of oil that should be in the engine, and the bottom one the type of oil. The engine oil is filled through this point here, where there's a dipstick giving us an indication of its level. We now proceed up onto the main rotor head area. We can use this step here in order to get up to inspect the swash plate. We check the play in the rotating scissor by moving the swash plate arm fore and aft. You're allowed 60,000ths of an inch, and this will give you an indication of play in the rotating scissor here. We need to run our hand along the top of the swash plate boot to make sure that there are no holes or cuts. We have a cord arm here with a weight. This allows us to balance the rotor head cord-wise. If we have a look at the main rotor pitch link, we're checking that the bearing is free without looseness. The witness marks are all in place and the pitch link is wire locked. We need to make sure that we have witness marks on the nut, in this case, of the coning hinge, also the split pin through the nut. We have some neoprene stops under here to prevent the blade being pushed down lower than the tail boom. We have static stops in here that prevents the blades from drooping when the centrifugal forces are removed during shutdown. In the grip of the blade, we have the pitch change bearings for the main rotor. They run in red Dextron transmission oil, the same oil as we have in the freewheel unit. The oil is held in the grip by this rubber boot, and we just check for leaks from this area here. And coming down here, we would need to look at the pitot tube to make sure that no bugs have climbed inside and blocked it. We need to inspect the blade, so we do that by bringing this blade to this position here. Pushing up on the aft blade will bring the forward blade down to a position where we can easily inspect it. So we're now to inspect the leading and trailing edges, the lower and the upper surfaces. Once you're happy with the condition of the blade, you need to push this blade up, rotate the blade to bring the aft blade forward so that we can inspect the other blade. Now let's have a look at the nav lights and do a symmetry check on the aircraft. This is the port nav light. The colour is red. The starboard nav light, which is green. On the rear of the aircraft we have the white position light, and on the top of the tail boom we have the red strobe light. It's a good idea now to do a symmetry check on the aircraft. Just stand back, and in this case we're looking aft, and make sure that the aircraft is standing square on its undercarriage. Remember that a thorough pre-flight inspection and a good understanding of the helicopter that you fly is all part of flight safety. Fly safely.